So today I will share the talk with Frederica that graduated about 1 month ago, and I thought that it would be much better if it's her that present the part on dynamic rupture propagation. So today we would like to discuss the mechanical behavior of lubricated fault, nucleation and propagation. And as I said, I will share this talk with Frederica, but this is also part of the PhD thesis of Paglialunga that is currently now postdoc in ING Europe, and the contribution of François Pascal that is now CNRS in Nice. So as you know, climate change mitigation strategies such as CO2 sequestration, extraction of less carbon intensive sources of energy, such as natural gas, geothermal energy, are important topics in science that can be partially solved by modern rock mechanics. And at AMR lab, we try to answer the following question: which type of energy should be developed in the future? And now with a big focus on deep geothermal energy, what is the future and feasibility of carbon capture and storage? What should we do with nuclear waste? And of course, we try to answer what are the risks associated with this new type of energy. On the diagram on the left, you can see that most of this energy are associated with fluid injection or extraction. However, fluid injection and extraction can increase pore pressure along fault and reduce normal effective stresses and reactivate fault, alter subsurface stresses, and alter the chemical and thermal properties of rock. Therefore, they can encourage seismicity. So fluids play an important role in fault zone and in earthquake generation, and these earthquakes are due to slip on pre-existing fault surfaces. So therefore, friction, fracture, and geometry are the key to understand the physics of natural and induced earthquake. On the diagram on the left, you can see that the rupture velocity during earthquake propagation is around 3 km per second, and slip velocity is around 1 meter per second. This earthquake can occur at depth, at a pressure around 200 MPa and temperature that can go up to 300 degrees Celsius. Therefore, seismology gives only indirect idea on what's happening directly on the fault plane and give only limited information. And today we would like to show you that laboratory seismology can bring further insight on what's happening on fault plane during induced earthquakes. This is a very famous diagram from Helfer 2013, where you have the number of earthquakes with magnitude higher than 3 versus time. Fluid injection started around 2007 and are followed by an exponential rise of seismicity. More recently, people discovered also that fluid injection can trigger a seismic slip, meaning that the elastic energy that is stored in the crust can be released in an aseismic way without radiating wave. This is a very famous example from California, where the aseismic slip is depicted in colors. Moreover, fluid injection can trigger primarily aseismic slip, and then seismicity is induced as a secondary effect. And this has been recently shown by Guglielmi and Viscous. So we also know that it exists different types of earthquakes: regular earthquakes that scale at a power of 3 between the seismic moment and the duration, and slow earthquakes where the scaling is of 1. And these earthquakes are very often associated with high pore fluid pressure at depth. So therefore, we think that also pore pressure can control rupture propagation. So the factor that influences induced seismicity can be divided in 3 categories: stress, geometry, and fluids. So in terms of stress, the parameter that control the induced seismicity are depths, the nearness to critically pre-stress, the natural size distribution, and in particular the B-value of the Gutenberg-Richter laws, the stress and fracture heterogeneity, and the background seismicity. In terms of geometry, of course, the rock type and the heterogeneities influence a lot seismicity. And there is a parameter that we can control when, for example, stimulating reservoir is the fluids. And in particular, we can control the injection volume, the fluid rheology, and the fluid chemistry that we inject to stimulate our reservoir. And today, I would like to focus on one parameter that is the fluid rheology, and in particular, the viscosity of the fluid. on the diagram on the right, you can see the different type of viscosity we can encounter in the crust, going from very low viscosity of 10-1 when it's dealing with CO2 up to 10⁻³ when we deal with fracturing fluids, and in particular when we have propans. So when we have viscous fluid on a fault plane, this can be explained by what we call the lubrication theory or the elastohydrodynamic theory. And the apparent friction coefficient, the dynamic one, can be expressed as a function of what we call the Sommerfeld number. The Sommerfeld number is simply the viscosity in Pascal per second, the slip rate in meter per second, the effective normal stress, and the geometrical factor. And this, depending on this Sommerfeld number, the dynamic friction coefficient can strongly drop and reduce the friction coefficient. In particular, under boundary condition, the load is mainly supported by the asperitic contact, so solid-solid contact, and the Sommerfeld number is lower than 10⁻⁻³. And in this case, the dynamic friction coefficient is almost equal to the static friction coefficient. And in case of rock material, that means that the friction coefficient is around 0.6, 0.85, following the Bayerly rule. Under hydrodynamic condition or fully lubricated condition, the Sommerfeld number is higher than 1, and in this case, the load is entirely supported by the fluid, and the dynamic friction coefficient is almost equal to the friction of the lubricant if it's liquid, and in this case, it can be around 0.1. And in between, the load is supported both by the fluids and the solid asperities, and we have a Sommerfeld number that is between 10⁻³ and 1, and in this case, the dynamic friction coefficient is in between the static friction coefficient and the friction coefficient of the lubricant. So today, I would like to show you with two types of experiments. The first one I will explain you, the second, Frederica, how this viscous fluid can influence friction, and if really in rocks during the earthquake, we can follow the elastohydrodynamic theory. So I will start first with the high velocity friction experiments. So in the case of our experiments, we use 4 types of fluids. The first one is pure water with a viscosity around 1 millipascal per second, and a free mixture between glycerol and water, 60% glycerol and 40% water, that give a viscosity around 10 millipascal per second, 80% of glycerol, 50% of water, that give a viscosity around 100 millipascal per second, and 90% glycerol, 1% of water, that give a viscosity of 1000 millipascal per second. So we have 4 order magnitudes in terms of viscosity, and we use glycerol because it's a Newtonian fluid, and that means that at a given temperature, the viscosity remains constant regardless of the slip rate. So the viscosity we use are representative to what we can have in a georeservoir, as I showed you before. So what we did is that we perform high velocity rotary shear experiments in a rotary shear machine that is called Shiva, that is based in Rome. The machine is divided in 2 parts. The first part is the rotary part that is made of a brushless engine and that allows to spin one sample on the others. The second part is the part where we can apply the load, is driven by a simple hydraulic pistons, and this allows to control the normal stress. We perform our experiments with westerly granite that you can see on the picture on the bottom on the right, but also on Carrara marble. The cylinders are about 50 millimeter diameters. The normal stress was 10 millimeter. We imposed a velocity function with an acceleration of 6.5 meters per second, a target velocity that can change, and a deceleration of about 6.5 meters per second as well. The pore pressure was kept constant at 2 megapascal, and we run the test under drain condition, meaning that the pore fluid pressure cannot increase a lot during experiments, and we have pistons, so a pore fluid pump that regulates the pressure if we have overpressurization. During the experiment, the recording rate was about 20 kilohertz per second, meaning that we had 25,000 points per second in terms of data. So this is on the right, one example of friction versus slip curve. So what I wrote is the shear stress on the normal stress, so the apparent friction coefficient versus slip. And what you see is that we have a first elastic increase of this apparent friction coefficient up to a peak value around 0.8, 0.9, that is followed by a huge weakening until we arrive to a steady state friction. This steady state friction is reached after a critical distance that I call DC on this diagram, and that is depicted by these green circles. As I said, we use for mixture of water and glycerol, and we use two types of material, westerly granite and Carrara marble. And before the experiments, we imposed a constant roughness on our sample with a RMS of about 30 micrometers per second. What I forget to tell you is that in the Sommerfeld number, the geometrical factor, that is the L on the H square, depend on the asperity size, and L is really the maximum wavelength that we can have on the full planes in terms of asperity, and H is the height of the asperity. So it's for this that at the beginning of the experiments, we take a lot of care in imposing the roughness on our sample. Then we run our experiments at different velocity from 10 micrometers per second to up to 1 meter per second. And we run about 40 experiments. Of course, when we are doing friction experiments, we produce shear heating on the surface of the sample, and the temperature increase during experiments. So to plot our Sommerfeld number, we need the viscosity that is temperature dependent. And what we did is we did a small model to compute the temperature on the full plane, and then following the empirical formulation of Cheng 2004, we correct the viscosity by the temperature. So like this, we have really a viscosity that is calculated with the temperature on the full plane, even if we have shear heating. So these are the results. And what you see is the dynamic friction coefficient versus the Sommerfeld number for both the westerly granite sample that are the diamond, triangle, and square, the purple square, and for the Carrara marble that are the yellow squares. And we run the test under dry and water condition, but here I plotted only the fluid condition, not only water, but only the fluid condition. Otherwise, you cannot plot the dry condition with the Sommerfeld number. And what we see is that our data really follow the elastohydrodynamic theory with a friction coefficient around 0.7 at a very low Sommerfeld number when we are under boundary condition, and very low dynamic friction coefficient when we are under hydrodynamic condition, fully lubricated condition, with Sommerfeld number higher than 1. In between, we have a huge decrease of this dynamic friction coefficient, so between the Violay friction coefficient and the friction coefficient of the lubricant. And we can model our data with a Lugre model that link the dynamic friction coefficient to the friction coefficient of the lubricant and the static one. So what is interesting is that if we look at the full surfaces after deformation, and we went to the profilometer, we measure the asperity size, we see that on our mixed lubrication coefficient, the asperity have a RMS of about 126 micrometers at the end. This is much bigger than what we had at the beginning, and this is because our asperity melted during deformation. So that means that we were really under mixed lubrication condition because part of the load was still supported by the asperity, and we can have frictional heating at the asperity and melting and increasing of this asperity size. If we do the same under fully lubricated condition, what we can see is that the RMS is about 36 micrometer. And this is exactly the same as what we had at the beginning of experiments, meaning that the asperity has not been affected by deformation, and this is because the load was fully supported by the fluid and not by the solid contact. So really, we can really depict, when we have a lubricant in between full surfaces, we can really depict the behavior of the fault in terms of friction with the elastohydrodynamic theory, and this really follow a strip-back curve with a dynamic friction coefficient going from a Violay friction coefficient to a friction coefficient of a lubricant. What is interesting is that if we plot this DC, that is the distance to reach a steady state in terms of friction versus the Sommerfeld number, we see that this is not a monotheous function of the Sommerfeld number, but we have an increase of DC under boundary and mixed lubricated condition and a decrease under hydrodynamic lubrication. So this has consequences on the breakdown work. Okay, if we calculate the breakdown work, that is the energy necessary to continue to propagate a rupture, that is simply the integral of the shear stress curve with the slip over a distance DC. What we see is that this breakdown work, WB, increase under boundary and mixed lubrication condition and decrease abruptly under hydrodynamic condition. Is really this breakdown work that will, if it's very big, that will probably impede the rupture to continue to propagate. So having a very big lubrication condition, very big breakdown work means that it will not be very easy to continue to propagate the rupture. So if I summarize a little bit, what we have seen is that the dynamic friction coefficient is affected by the presence of fluids, as well as the breakdown work is also affected by the type of fluids. When we had the water, we had a slightly different strip rate curve than under glycerol mixture condition. We show that when viscosity increases, the dynamic friction coefficient decrease, but the breakdown work can increase. And when we increase velocity, the dynamic friction coefficient decrease following elastohydrodynamic theory, and the breakdown work increase. What I want to remind you is that the RMS, that is the asperity size under fully lubricated condition, is of the same magnitude as the initial sample, and this confirms that we are really under fully lubricated condition, that the slip necessary to reach the steady state is a function of the lubrication condition with a small with a DC that increase under boundary and mixed lubrication condition and decrease under fully lubricated condition, and that the boundary the breakdown work necessary to reach the steady state increase also under mixed lubrication condition and drastically decrease in fully lubricated condition. And this is quite funny because you can have a very, very small friction coefficient under mixed lubrication condition. Is probably the smaller friction coefficient we have, but is the higher breakdown work. That means that also if we have a lubricant, that doesn't mean that we have a easier earthquake propagation with this very large breakdown work. Now, we try to see if what we find with this mixture of water and glycerol can also explain other rotary shear experiments when we had frictional melt, so a kind of lubricant and viscous fluids in between two plates. For this, we plotted all previously published data with this rotary shear where we had frictional melt on peridotite, tonalite, gabbro, and microgabbro, and you can see that we can pretty well plot the data on the same curve, and they all follow the same curve, dynamic friction coefficient versus Sommerfeld number. So we can also explain previous data where we had frictional melt that developed by elastohydrodynamic theory. We try to do the same for two very well-known outcrops where we can find pseudotachylite. Pseudotachylite are frictional veins where we can, so paleo earthquake where we had frictional veins melting during earthquakes. And these two spots are very well known in terms of geometry of the fault, paleo stresses, and we computed so the dynamic friction coefficient and Sommerfeld number for these two places with an hypothesis that the velocity was around 1 meter per second, which is, I think, an hypothesis that is not absurd in the sense that this is often thought that earthquakes propagate at 1 meter per second. So we computed and we see that we can also explain paleo earthquakes with the hydrodynamic theory. We try to do the same for induced earthquake, where we know the viscosity of the fluid that is injected, the normal stress, and also here we make an hypothesis of slip velocity of 1 meter per second, and we can pretty much explain all induced earthquake, or at least the dynamic friction coefficient of these induced earthquakes with the hydrodynamic theory, except for one spot that was the Boylan shale, and we were not very surprised because I think in shale the mechanisms are a bit different. So if I try to summarize this part, what I show you is that we reproduce in the lab the nucleation and a little bit more the co-seismic weakening and propagation of seismic lip in absence and in presence of fluid with varying viscosity. We showed that fluid viscosity can promote earthquake nucleation and that elastohydrodynamic lubrication theory is a valid weakening mechanism that could be that can explain the dynamic friction weakening in presence of fluid. So we can explain full weakening with this EHD theory, and that viscosity is an important parameter that can control in part seismicity during fluid-induced earthquakes. So this was really the part on friction, and I think earthquake is not only friction but is also dynamic rupture. And now I would like the floor to Frederica to explain you what we have done on dynamic rupture with viscous fluids.
Yes. So following up the work of Chiara and Marie, I also wanted to try to study the influence of fluid viscosity on dynamic rupture experiments. So different experimental setup to study the same parameters, so fluid viscosity. So the setup is quite simple compared to the apparatus that Marie just presented to you. It's a biaxial direct shear apparatus. As you can see here, the two samples are highlighted in yellow. You cannot really see them because they're transparent. So there are basically two blocks that are pressed one against the other through two hydraulic pumps, and then they are sheared in a second stage in order to reproduce dynamic ruptures, so laboratory earthquakes. So why do we use plastic? We use PMMA because it's homogeneous and an isotropic material. Moreover, its elastic properties are much lower than the one of rocks. That means that we can have much larger deformations that are easier to measure in the laboratory, and we can have longer effective fault lengths. For example, the nucleation length of a rupture for plastic, for PMMA, is much lower, much smaller than the one that we would expect for rocks. That means that for the same apparatus, we can see much more in detail the dynamic propagation of the rupture. And then on top of that, this material is transparent. That means that we can use imaging techniques, as I will show you in a bit. So for what about the sensors? We had strain gauge placed all along the fault in order to measure the deformation along the fault and to track the rupture fronts, nucleation and propagation. They were recording at a very high recording frequency of 2 megahertz. And on top of that, we also had 2 accelerometers on the right side of the fault that allowed us to measure acceleration and to estimate slip and slip rate of our ruptures. Then we used the fast camera, as you can see here in the picture on the left. That allowed us to use photoelasticity. So photoelasticity is a very powerful tool that allowed us to track the nucleation and the propagation of the rupture front. And this works very well for birefringent materials. That means that our materials like PMMA, the one that we use, that are optically isotropic when there is no stress applied, but under stress. So once loaded, they become optically anisotropic. And as you can see here on the right, some fringes can appear and they will allow us to track the rupture front. So we basically performed 2 sets of experiments. The first set of experiments under dry conditions for increasing normal stress from 1 to 1.75 MPa to 3.5 MPa, and then a second set of experiments under lubricated conditions. So in this case, the normal stress was kept constant at 3.5 MPa, but the fluid, there was a fluid applied on the surface. So I just dropped some drops of fluid along the interface before the experiment, and this fluid had different viscosity values, and the viscosity values were just the same as the ones that were used in the study that Marie just presented to you. So they were spanning 4 orders of magnitude of viscosity. So as we saw already in the first part, we can have different lubrication regimes. Boundary lubrication, when the load is supported totally by the solid contacts. And we have a friction coefficient that is comparable to the one of the bulk material. Then we can have full lubrication when the load is supported totally by the lubricated contacts. And in this case, the friction is much lower, so comparable to the friction of the fluid. And then a mixed lubrication, which is in the middle. So the load is supported partly by the solid contacts and in part by the lubricated contacts. And the friction coefficient will also be in between the two. So for all these different conditions that we tested, we wanted to study different properties of the ruptures. So one of these is the frictional strength. So during our experiment, there was a first stage in which the normal load was increased and kept constant during the experiment. Then in a second phase, the shear stress was increased until, of course, reaching the fault strength, and we could observe the emergence of instabilities. As you can see here on the left, in black, the applied normal stress, and in gray, the applied shear stress. And each of these drops is what we consider a rupture and a laboratory earthquake. So to compare the frictional strength of all our experiments, of all our ruptures, we computed what we call here friction, which is just a ratio between the shear stress and the normal stress, which of course follows the same evolution of the shear stress. So now to compare this for all our conditions, we plot in what you see here the peak friction for every rupture occurring under each condition. So on the left, you can see the evolution of the peak friction with increasing normal stress under dry conditions, which, as you can see, is quite constant as expected. Of course, the peak friction you don't expect it to evolve to decrease or increase when increasing normal stress. And on the right, you can see its evolution under lubricated conditions for increasing fluid viscosity. And this was the first observation that we did in this study, is that the friction coefficient was decreasing. So slightly for the lowest viscosity, which is water, but more dramatically for the other viscosity values. And as I just reminded you before, this is an indication of mixed lubrication conditions. So from these results, we assume that the ruptures that we measured during our experiments were happening under mixed lubrication conditions. So all the observations that I will show you in the next slide, they will all refer to the case of mixed lubrication condition. So the second property of the rupture that we wanted to study was the nucleation phase, so the nucleation length. As I told you before, the use of the camera allowed us to treat the data through photoelasticity. So this allowed us to have a picture of the rupture front. So you can see here on the left, there are many images that are stuck one after the other in time in order to reproduce this light map. So you can see on the x-axis the position along the fault, which is 20 centimeters long, and on the y-axis the evolution in time. So in this kind of measurement, the light contrast indicates a difference in stress, a perturbation in stress. And so you can see around this portion of the fault, at the beginning of the event, there is something nucleating here. So there is a quasi-static increased growth of the rupture, then an acceleration, and then a dynamic propagation with the velocity, rupture velocity, which is overall constant in this case. So we had this kind of data for each rupture. And so what I did, it was just to handpick this rupture front and to study the difference for each conditions, under dry conditions and lubricated conditions. And so for each rupture, we could define what we call the nucleation length, which was in this case defined as the first observed slipping patch. So by looking at the nucleation length for all our events, we can build a similar plot to the one that I showed you before. Only in this case, we see the evolution of the nucleation length with normal stress on the left for dry conditions, and on the right under lubricated conditions for increasing viscosity value. So you can see that under dry conditions, the nucleation length decreases for increasing normal stress, as was expected by the theory, and it was showed through experiments by Soumaya Latour in 2013. And this is one of the common equations for estimating the nucleation length. And as you can see, the normal stress is at the bottom of this ratio. So it makes completely sense that increasing the normal stress, we will reduce the nucleation length. Now, what we observed for lubricated conditions, it was a bit less expected, let's say. And we can see that the nucleation length for the same normal stress of the last dry condition experiment here, so 3.5 MPa, is drastically increased. So it's doubled for water, and then it increased further for higher fluid viscosities. And this is most probably due to the fact that for increasing viscosity, we observed lower peak frictions and lower friction drops. And you can see here that the drop in friction is also at the bottom of this ratio. That makes the nucleation length LC to increase for increasing viscosity. Now, the third property of the ruptures that we observed was fracture energy. So we know that fracture energy is a very important quantity to describe dynamic ruptures, because it can control the rupture nucleation, as you saw just now in the equation before, the rupture propagation and the rupture arrest. It's very well known, the rupture propagation criterion, for which if the energy release rate, which is the driving force of the rupture, and is the energy that is available around the crack tip, is equal or larger than the fracture energy, which is an interface property, then the dynamic rupture is allowed to propagate further. And so we wanted to quantify this fracture energy for all the different conditions, and to see how that changed under lubricated conditions. So to do that, we followed the method, the protocol defined already by J. Feinberg and Svetlisky in 2014, that is assuming the frictional ruptures during this kind of experiments as mode 2 cracks, so using linear elastic fracture mechanics. So we know that under linear elastic fracture mechanics, as a crack propagates, there is a stress perturbation around the crack tip, and this stress perturbation can be described by one parameter, which is K2 in this case, because we are in mode 2, and is the stress intensity factor. So this stress intensity factor determines the severity of the stress perturbation. So we followed, as I just said, the protocol from Svetlisky and Feinberg. So as a first step, we defined the shear stress perturbation expected by the theory, by linear elastic fracture mechanics. And then as a second step, we compared our analytical prediction to the stress perturbation measured in our experiment. In this way, we could output a value of K, the stress intensity factor. And as the last step, third step, we could use this stress intensity factor to measure, to have an estimate of the fracture energy characterizing our ruptures. So you can see here on the left an example of our experiment. This one is under dry conditions at the normal stress of 3.5 MPa. So what's in the background is the photoelasticity data, and what is plotted on top of that in red is the data coming from the strain gauges. So it's mechanical data, it's evolution of strain with time all along the fault y-axis. And you can see in dash white the theoretical prediction coming from LFM. And of course, you can see that the predictions were made only during the dynamic propagation of the rupture and not during the nucleation of the rupture, which occurred here in this portion of the fault, because this theory applies only during the dynamic propagation. And then by doing so for all the experiments, okay, here on the right, all the fit for the other conditions, so under lubricated conditions, and here at the bottom right, you can observe the evolution of this fracture energy, which reaches value of around 1 joules per meter squared under dry conditions, and it dramatically decreased under lubricated conditions, regardless the viscosity value. So this means that the fracture energy under mixed lubricated conditions decreased. And this means that in this specific case, in these conditions, there is an easier rupture propagation. Then from the photoelasticity measurement, we could also measure the velocity of the propagation front, of the rupture front. And as you can see here, there are two main behaviors that come out. So what is showed in light blue is the evolution of velocity for dry conditions. And you can see that they reach values quite high, comparable to the railway speed. However, this is not good for the ruptures occurring under lubricated conditions, which are these ones at the bottom. They first increase with propagation length of the rupture, and then they keep propagating in a much more stable way, and then eventually decelerating or accelerating towards the end of the fault. And so this difference in behavior between dry ruptures and lubricated ruptures made us think about the rupture types that could have been different in the two cases. And so we computed the characteristic times, the race time and the source duration. So we know that these two characteristic time, they're able to indicate the type of a rupture. So the local slip duration is so if we are in one position, in one location along the fault, for example, in this red point here, the local slip duration is the duration of the slip that is occurring in that point. The rupture duration is the total expected duration of the rupture, considering its nucleation location. And so if these two times are comparable or similar to each other, this indicates that the rupture propagates mostly crack-like. That means that the interface keeps sliding in the wake of the crack tip. While if the local slip duration is lower than the rupture duration, this indicates that the rupture is most probably propagating under pulse-like, meaning that there is a healing front in the wake of the crack tip that closes the interface. And so you can see here on the right, we compared these two times for the different ruptures that we had in our experiments. And the dashed red line indicates the one-to-one slope. And so you can see that all the markers in light blue that indicates ruptures, dry ruptures, they fall more or less along this red line, meaning that the dry ruptures propagated crack-like, while all the other ruptures, all the other colors, so the green, the gray, purple, and dark blue, they indicate lubricated ruptures. And they all fall, or most of them fall, on the domain for which the race time is lower than the duration time, indicated that probably these ruptures occurred under pulse-like mode. And so it was the last observation, the last conclusion of this work. So now summarizing what the presence of a lubricant can do for dynamic nucleation and propagation of a frictional rupture. Under mixed lubrication conditions, it can reduce the frictional strength of the fault, meaning easier fault reactivation. It can increase the nucleation length of a rupture. It can decrease the fracture energy, meaning easier rupture propagation, and it can induce pulse-like rupture. So now concluding this presentation, what we presented, Mary and myself, is that we, in the laboratory, we can reproduce the nucleation, the propagation, the ecosysmic weakening of seismic slip with and without fluids and with varying viscosities. We showed that the fluid viscosity can promote earthquakes nucleation and that elastohydrodynamic is a valid weakening mechanism that can be activated for high viscosities. We showed that fluid viscosity can promote low rupture velocity and pulse-like ruptures, that elastohydrodynamic can explain fault weakening in the laboratory, in natural earthquakes with pseudotachylides, and in induced seismicity, induced earthquakes. And finally, that viscosity is an important parameter that should be considered to better understand fluid-induced seismicity. So once again, what we presented today is the work made by Chiara Cornelio during her PhD thesis, together with Francois and of course Marie and myself.